Good morning from cloudy Munich. I'm very happy that you all join us here today for this webinar. I hope you can see my screen. Today's topic, we talk about data centers and data center interconnect, and more specifically about simplified operation and maintenance of data centers. Because in the end, usability and ease of use and more intelligence are key to making these appliances ready for a broader market and to be deployed not just by optical experts, but by any IT technicians out there. So let's get started. If we look at the key aspects of self-built DCI or data center interconnect, we see there's three main criteria. One is space, and bandwidth demand, especially now in the pandemic, is increasing, at faster than ever before. And before we saw rates of 40, 45% year over year. And I think it's clear that we cannot, the space leasing fee cannot increase similarly. So the appliance to be used in DCI needs to provide over the roadmap of several generations, a high integration of components, a densification of interconnect, and just in general, to bring down the cost per leased rack unit in the data center. The second one is bandwidth and fiber usage. Because, of course, increasing the bandwidth demand on the rate of 40 or 45% year over year, it will be not sustainable if we wouldn't try to utilize the fiber more efficiently. Because if we wouldn't, the fiber leasing fee for self-built DCI can be very prohibitive. It depends on the exact location. Is it in a dense city? More outside. It depends on the distance of the fiber to be leased. But generally, adding an additional leased fiber to the system increases the cost, the operational cost dramatically. And an intelligent DCI platform or a system need to be providing a more efficient use of the fiber to the customers to enable for the next 3 to 5 to 6 years, a stable build out without the risk of leasing additional fibers. And last but not least, operation maintenance, O&M. Here, if we come from classical optical networking and we look at, how our nationwide, backbone networks being built and operated and installed, we see that this task typically was quite complex, and the kind of operation and configuration of the system often was manual or also very time intense, and more specifically required experts on the domain, optical experts. However, if an enterprise were to build its own small data center interconnect, these optical experts are hard to come by, and we need to be able to utilize this optical DCI platform with IT expertise. It needs to be as simple as Ethernet, plug and play, ready to go. So Huawei's DC908 solution is our latest generation of purpose-built data center interconnect. It enables really simple self-built DCI. First, space saving. So compared to the first generation of our solution, we increased the capacity in the rack unit by 50% to enable, more compact, more dense deployment and saving on the leasing space in a co-location. Second, and we already had webinars on this topic, is the ultra broadband capability of our solution. The latest generation offers 800 gigabit per second per laser, per lambda, and utilizing, so which is in its way more spectrally efficient than previous solutions. And actually this 800 gigabit per second can be offered in 100 gigahertz spacing. And if we then expand the utilized space, the bandwidth in the fiber, going from a standard C-band to a super C-band and also an L-band, meaning it's still the same fiber. We pay only once, but then we just try to squeeze it the most from it. We get to a total capacity of up to 88 terabits per fiber, utilizing 800 gig per lambda. But it's talking about capacity, talking about modulation formats and advanced signal processing reminds me of when in the 90s, my family bought its first VHS recorder. It was a very nice device. You can program anything, but I was the only one who could use it. I was a kid, and I had to help out my parents to program the VHS recorder. So same thing here. You don't want to be stuck with a beautiful technological marvel, but at the same time, it will be hard to operate and hard to maintain over its runtime. This is why simplified operation maintenance is a key feature of these platforms. It needs to enable any IT engineer with basic data center and server experience to install and operate such a platform. Already in the first generation of our product, we have been able to provide full automation of auto commissioning within less than 8 minutes of a system. It's plug and play, zero touch. It provides also a simplified network level web GUI, which strips away all the complexity that is usually attached to the classical optical network management systems. It needs to be simple to operate. It needs to be easy with one click. Now, in the second generation of our product, we invested in the intelligence of system monitoring. On one hand, we offer advanced fiber health prediction, which is a topic we will talk about later. We also talk about co-bundling fiber cable detection, what it is and what it means to the user. System offers accurate troubleshooting, because if an error happens, you need to know exactly where the technician needs to go and locate and make the fiber patch. And again, we have a simple web GUI interface to visualize fiber fault location and to instantaneously monitor whether fiber cut has been fixed and what the performance of the upgraded fiber patch is. So let's dig deeper in simplified O&M. So as I already said, we go now from a first generation of automated DCI, which is very IT oriented. It's designed for not optical experts, it's for IT technicians. This platform is as simple as install a server. And the optical fiber is the equivalent of an Ethernet cable. And now we go towards from passive O&M, where we have seen, especially in dense cities, that major losses can be caused by fiber faults. Fiber faults are one of the major impairments on running a system. And after fault occurs, the question is, how fast can we locate and solve this issue? So we go from this mindset, this old school approach to running optical networks, to a proactive O&M. We see we have a new tool offering fiber health prediction with more than 90% accuracy, meaning that we want to really minimize the false positives, because you don't want to dispatch your technicians like too often, because otherwise you would spend more money on these false positives. In this case, the prediction is very, very accurate. And proactively, one can engage with the network and fix fiber before a default and loss of traffic actually happens. This is what you see down on the left bottom. We see how the system automatically monitors various parameters. Yeah, and I think the question is also not just which parameters to monitor, but how to analyze these parameters. Because just to extract them and to say, well, we are approaching, we have less than before, does not necessarily tell us about when a fault is likely to occur. And this is the key information in this case, because we don't want to fix these errors like half a year in advance. And in this case, we see that at the present, for example, the system can predict with a certain confidence an interval where an error could happen, therefore giving the user sufficient time to go to the network and fix the cable. Also, more importantly, so we have these slow degradations of the fiber. There's also different effects. For example, a fiber can be just cut abruptly, and in this case, where there's a excavation going on, construction work, detection, like a millisecond level detection of a fiber cut, which is in the way it's happening, can also be crucial to reroute the traffic in time and actually not lose any customer data on the higher layers of communication. And on the right, we see the core route detection. What does it mean? It's an interesting use case. It means that, for example, as we spoke about, fiber cuts can happen, right? I mean, we can have construction sites and these workers may not know the exact layout of a fiber network. So they can cut the fiber. And these things happen all the time. So one needs to build a network which is resilient against fiber cuts by nature. And what the users do, they build in a protection path, as one example. But often if we also lease fiber, and it can happen that the exact routing of the protection fiber is not fully known. And in fact, there can be cases where the protection fiber and the actual active fiber can run over the same duct, the same cable. And then of course, a cut occurs. This has catastrophic consequences because the user is not prepared to address a fault which happens to both the active and the standby cable. But how does the user find out whether the fiber plant is actually totally independent? Because sometimes just no records, or the records are faulty, or the records were done written down manually, but not really digitized in time. I mean, there's really a lot information which can be lost from the 20, 30 years ago when the fiber was deployed. So let's first look at fiber health prediction. One important aspect is a parameter. A number you have to remember is that fiber faults account for a majority of outages in WDM networks. It can be as high as 68 or 70%, depending on the country and the continent, depending on how dense the population is, depending on how fast, let's say, a city is growing. And what we offer in our system is active monitoring and proactive performance assessment. We have built in OTDRs, optical time domain reflectometers, which send impulses into the fiber, measure the reflections which come back. And for example, these reflections, with these kind of reflections, it's easy to locate a old patch, for example, or a space where there's just more loss than there should be. And then based on these observations, which is it's not just the OTDR, the system also monitors other advanced parameters in the fiber, like the OSNR, signal to noise ratio, the optical power, the total fiber loss, the bit error ratio, which the modem signal to network management. And with this monitoring, one can send out a warning, which will say in 1 hour, or in a day from now, in 2 days from now, in a week from now, a fault is likely to occur, thus giving the user sufficient time to go and send out a technician to the field and to fix this fault in a way which doesn't really affect the traffic. Maybe it's the maintenance window, maybe the user can reroute the traffic otherwise while the fiber is being fixed. But I guess the key is knowing this beforehand takes out all the stress from fixing the fiber, patching the fiber, because it's then it's not just about where every minute counts. We have time to go out and do the maintenance. And also, more importantly, now for those of you who may have seen old-fashioned and old-school network management systems, visualization of a fiber health or the network health is not really, kind of inherent feature. It was strong in the old times. So it was usually one need to click into every network element to find out what's going on in there. And here we have really simplified visualization of what's happening in the network. It's easy to read out the reports, which are generated automatically. It's easy to visualize potential degradation, potential risks, potential alarms. So this is really made all for the usability of IT and not for optical experts. So as I mentioned, one key to this intelligence is the sensing. We have sensors built in the whole active network, and which happens in the transceivers. We can monitor the actual optical power going in or the received power arriving at the receiver. We have built-in spectrum monitoring, which can analyze the spectrum shape and derive the optical signal to noise ratio. We have OTDRs, which can measure the fiber loss change along the system. But all of this data in itself is helpful, but not really useful as it is just to come to a prediction. What we need is a second layer of machine learning, where based on big data training from the various many networks in the world which Huawei is operating, from all the experience that we gathered along the last 35 years of deploying optical networks, we trained these machine learning algorithms to, on runtime, arrive at very fast and accurate predictions. So the key is sensing and machine learning. These two together can provide these predictive algorithms. So we have the first step is detecting the fault, and it happens, automated measurements happen over time. Locating the fault, because where exactly does a technician need to go in to patch the fiber? That's the key question. The fault recovery. So, do we need to send somebody back and ask someone to go and plug in the OTDR device and measure the fiber loss? No, in this case, it happens automatically. We patch up the fiber, we can instantaneously, through the built-in OTDRs, monitor in the system what the new fiber loss is, whether the patch has been done successfully. So the automated instantaneous measurement of the fiber quality really simplifies the maintenance for the technicians in the field. Then, of course, periodic quality reports, which summarize the state of the network as it is and give the user a good feel about what's happening in the network over the course of its deployment. All right, so on the next slide, we'd like to show you a short video about which visualizes some of these key aspects again in more detail.
Nearly 70% outages are fiber fault, causing massive users interruptions disruption. NCE uses big data to perform AI-based analytics and optical health prediction and proactive maintenance of fiber degradation and interruption to minimize service disruption. Sub-healthy fibers are prioritized and recommended for quick resolution. After root cause analysis, ensuring zero service downtime. With millisecond-level detection capability, fiber interruption can be predicted hundreds of milliseconds in advance, and the temporary protection route will be set. Affected services recover within 50 milliseconds upon fiber failure to ensure end users' experience.
All right, so you have seen also the quickness of analysis in case there is a cut happening can be crucial to network resilience. So if we look at the next slide, it's we just wanted to visualize for you how it all looks like in the system, how it actually, what the user sees. So the first step, we see a kind of a time evolution of a certain fiber link. We see that for a period, during the day, the fiber was categorized as sub-healthy. We have to see this yellow color here. And at some point, the trigger happens, the system predicts an outage in the near future, and the indicator turns to red. So we have here a predicted fiber failure, and an alarm is triggered. So the technician can be dispatched to go and fix the fiber. Now the question is, where does the technician need to go? We have, through the integrated OTDRs, we locate exactly to the meter the actual location of this degradation effect in the fiber, enabling the technician to go in and patch it up exactly when it happens, or where it happens. And the technician can see the fiber loss at this location before and after, instantaneously. So after the cutover is performed, and we see a green indicator in the system, the technician can also see, from a previously maybe 1.8 dB degradation, the fiber went up to, we removed 1.6 dB loss from the system. We're left with only 0.2 dB, which is an okay value for a splice. And the system is back up with sufficient margin. And then we would see in the fiber monitoring tool that at this time, the indicator is turning to green, and the system is considered healthy. So and then these records are automatically stored in the periodic reports which are provided. So of course, we know that the duration of such an interruption is an important indicator of or important performance criteria, KPI, for the default clauses signed by the enterprise and the network provider. Ideally, there should be no outages, or if they happen, should be as short as possible. One cannot allow for hours and days to go by before a cut is fixed and localized. And with this proactive, predictive monitoring, the system runs smoothly, and the disruption really is minimized to very small level. Now, the second aspect, which I want to talk about today, is co-route detection, which can really significantly improve the survivability of optical networks. So what does it exactly mean? On the left side, we see a customer who leased 2 fibers, and the leased 2 fibers with a goal, for example, to have a geographical distinction between these 2 locations, the geographical diversity, to, for example, have a working path and a protection path. In case then the fiber from the green one from A to B, C is cut, the orange fiber can route the traffic with minimal disruption. However, as I previously said, sometimes these records are not complete or available. For historical reasons. Some data may be lost, or you may see that the operators may have been bought by different companies, and then in a transition of the IT, you never know. So, what happened 30 years ago sometimes it's hard to document. So in fact, it's actually a valid use case. We have seen it to be very critical that there's not a full knowledge about the exact locations of these fiber ducts, especially in densely populated cities. That actually can happen that the active and standby cable run through the same physical location. And if then a fiber cut happens, this can have catastrophic events. We have seen here, so we have here 2 examples on the right. One example in China, a overseas over-the-top network provider was disrupted for 11 hours in its service because exactly this error occurred. Obviously, no one wants to have such a long disruption, because if such a disruption happens, usually the CEO of your customer is calling the CEO of the operator. And then, it's really escalating very, very quickly to the highest levels. And these kind of risks are inherent to these networks. And often, users only find out about it when the fault happens. So what can we do to prevent this from happening? How does the user who leases the fibers find out more about where the fibers actually are? Is it even possible? I mean, we cannot dig into the ground, right? Well, the beauty of fiber sensing is really such that one can use effects which happen in the fiber to make such predictions. For example, we can have vehicles passing through, or high-speed railways. Often the fibers are deployed next to railways, causing vibrations, right? Also, construction sites can cause vibrations. So anything which causes a difference in the environment of the fiber, let it be vibration, let it be temperature, let it be even a lightning strike. Now we have seen that in optical ground wire cables. These ground wire cables are deployed in these power distribution systems to actually protect the power lines against lightning strikes. But a long time ago, people figured out, hey, this is the best way to put a fiber in the ground wire cable where the lightning strike is hitting. Because for some reason they assumed the fiber is not impacted by electromagnetic fields outside of the cable. But it is impacted. Everything is impacted. Everything causes a change in the fiber. And the beauty is we can monitor these changes using various effects. For example, a lightning strike in the optical ground wire cable, so kind of overhead cable, causes a change in the polarization of the signal. And actually here in Munich, we have analyzed this effect to the fullest, and we have gone to like a lightning laboratory, creates really these very strong lightnings to measure what happens in the fiber. So we know that there's an observable, quantifiable, and direct impact from an event, a vibration, lightning strike, a thermal change on effects which happen in the fiber, maybe Rayleigh scattering or Raman scattering, as long as we can monitor them. So we do monitor them through integrated sensing systems. And we can actually assess, for example, if we see a disturbance in one fiber and the same disturbance happens in the fiber which is supposed to be geographically distinct from the original fiber, we know they must be, with a very high certainty, in the same physical location, in the same cable, in the same duct. By the way, so these kind of sensing can also be quite interesting for natural monitoring. You may have read about subsea operators who can monitor earthquakes actually using fibers. I mean, it's an amazing technology. How can a very tiny fiber on the ground be used with such an intelligence to monitor the surroundings? What is happening around the country or the sea? But it is possible. It is possible. So with this kind of integrated and automized intelligence, we can detect whether a fiber is actually correlated with a different fiber. So let's look at a second short video which visualizes exactly this measurement technique.
Can we help Enterprise Data Center identify the network risks related to co-cable services? iMaster NCE works with Huawei OpticStrand's DC908 devices to provide a solution for identifying co-cable fibers.
We can see that two groups of optical fiber connectors on the table are connected to two optical cables of different lengths. We can see that the service's working and protection fibers are located in both optical cables and are in the normal state. Open the Co-Binding Fiber Cable Detection app to view the check result of the service's working and protection fibers. The result shows that these fibers do not share the same cable. Next, adjust the fiber connector and connect the working and protection fibers to the same optical cable. Let's check whether iMaster NCE can detect the change. Perform the check again. We can see that iMaster NCE successfully identifies the risk presented by the working and protection fibers sharing the same cable. In addition, key information such as the co-cable distance is provided to facilitate service rectification.
All right, so we go to our last slide. This was we didn't want to overload this webinar with too much information. This is an important slide because, in the end, depending on the geography, topology, and the continent, fiber networks can look really different, the fiber plant. And we have analyzed with an operator X, its actual fiber plant. We have seen that for several different scenarios, there is risk in the system. For 1+1 protection service with a main and standby fiber, which is supposed to be geographically different, it was identified that around 17% of these fibers actually run at some point, not the whole distance, but they can maybe share 2-3 kilometers of the same cable, same duct. They are not fully geographically distinct. Also, in networks which employ point to multi-point services, where we can it is assumed that the traffic from A to C, if there's an outage in A to C, then A to D and A to B would not be affected. We can also have shown here that see here 28% in this case in this network element, there were instances of kind of these three logically distinct paths being co-routed before they actually leave and go out to these different geographical sites. So also here we identified clear risks which are closer to the network element of a potential outage which could actually hit all the services and not just one. And last, we've for rings, we logically the user assumes that if the traffic in the east direction is cut, we still have the west path, to route the traffic from, let's say, instead of A to C, from A to B to D to C. But also here, the logical design and the actual physical reality are not the same. And we have shown for this operator that in 32% of the cases, there was at some point a short co-routing of logically actually independent ring fiber spans. So also here there was a risk that an outage could happen, which could have catastrophic events. And the only way to find out if we don't have information about the exact fiber location is by using advanced fiber sensing, which one can do in this case. All right, so with this, we'll end the webinar. So thank you very much and have a great day. Goodbye.